Just a quick recap of something we did early. Because this totally anticipates the rotations. Okay? This transformation here, you define a transformation by this matrix, has the effect, if you multiply things out, you can see pretty easily, of rotating everything in the plane through, should be 37 degrees, okay? Or is it 53 degrees? 53 degrees. Okay? Now you can do that by just multiplying A by a set of unit vectors around the circle. And you see that A applied to the vector 1, 0 gives you the vector 0.8, 0.6. Okay. And 0.8, 0.6, 0.8 in this direction, 0.6 in this direction. And that is at 37 degrees. My picture doesn't look like 37 degrees. Roughly 37 degrees. Okay? So we'll see exactly what it ought to be. Because, yeah, that's right. Like I say, stuff I ate just a few minutes still has to get to my bloodstream and my brain. Waited too long to eat. Okay. One time when I've had a valid excuse for being stupid. Okay, and that was kind of stupid. So we do this transformation and we do this transformation. Okay? And this transformation just expands things to stretches in the x direction by factor 2, the y direction by factor 3, but it also reverses. Okay? So what you've got here is a rotation. Just rotates the whole picture. You can see the purple goes to purple, green goes to green. Everything rotates this way. Okay? This one takes the same picture and just stretches everything by factor of 3 in this direction, factor of 2 in this direction, but also inverts it so that this vector gets stretched by factor of 3. It doesn't really look like a factor of 3, but it also goes on the opposite side. And these things are numbered, 1 through 12, and here you got 1 through 12, so you can clearly see the rotation. Okay? And all this is just based on what happens to these unit vectors. And these are equally spaced unit vectors. Okay? You know, this vector is in the x-axis, this vector is at 30 degrees, this vector is at 60 degrees, this vector is at 90 degrees. Okay, just to remind you of the picture. If we compose these two transformations, okay, if you follow T1 by T2, if this is your T1 transformation, and this is your T2 transformation, then you do T1, you rotate, and then you stretch everything. What happens? Well, if you rotate all these and then stretch it, you get an ellipse. Okay? And your eigenvectors are going to be pretty obvious. Okay? Because the eigenvectors of this are really obvious, eigenvalues. So that's kind of where we head with this idea. But follow T1 by T2 means your matrix is going to be T2 times T1. Okay? Because T1 is the first one that acts, then T2. Then I ask is T2 times T1 equal T1 times T2? And that's generally not true because matrix multiplication, as you know, is not commutative. If you follow T2 by T1, that has the effect of rotating the ellipse that you get down here because these vectors kind of define a circle. They're representative of vectors around a circle. It's going to be an ellipse. okay? So if you do this transformation, T2, and follow it by the transformation T1, which rotates everything, we get a rotated ellipse, right? Now, in this case, it might be, it probably isn't. You can think about it. That if you first rotate and then apply this transformation, stretching everything by factor 3 here, inverting it, and then factor 2 here, it'll give you the same ellipse. Okay? Other things you can see here, the determinant of this matrix is negative, and the sense in which you go around the circle is reversed. You go around the ellipse clockwise when you go around the circle counterclockwise. The area of this thing is 6 times the area of this. Twice as big this way, 3 times as big this way. It makes sense, but you can prove it. Okay? The area of this one is the same as the area of this one. The area of this thing is clearly 1, 0.64 and 0.36. Okay? So there's a whole lot of implications of this picture, which is why I usually start the course with it. Okay? The relevance to what we're looking at right now is just matrix representation of a transformation. Okay, so if you define the transformation to be a 37-degree rotation, there's your matrix. Okay? If you define the thing to be a stretch and reflection here and a stretch here, those appropriate numbers will be in the diagonals. You have this kind of matrix. Combine them, you get something different. Okay? Okay. So, and you know, the matrix we get if we do this transformation, and then this one is here. It's going to also have a determinant of -6. Okay, because this one preserves areas, and this one gives you 6 times the area. Okay, it's also going to be your orientation, your sense of going around a curve is going to reverse. Determinant's negative, tells you that. Okay, so let's get a preview. Let's go back to representations and the thing we were going to talk about, which is rotations. But this is a good illustration.